All right, recorded is rolling. Welcome to Wednesday, September 6th. All right, so since there's a bunch of testing going on today, we're going to go ahead and postpone this lab. Now, you guys have the equipment on your desk so you can see it up close. Yeah, so you get an extra day to think about how that's going to work. Remember, tomorrow, I'll take you guys outside on the balcony and have you guys fire those projectile launchers horizontally, spot where the ball lands, and from that you'll be able to determine the blast speed of the launcher. Well, that combined with you'll know the height of the balcony because you'll measure it. Okay? But here we're doing. So we're going to do change plans today. Here's what we do instead. We'll do conceptual questions through Kahoot. Some of you guys already logged on before I hit record. So we're about to switch over and knock those out. Just right here on the board. And through part of an FRQ on your desk. So we'll do an FRQ activity. I'll walk you guys through one. I found one that involves a projectile. So we'll do that. And then whatever class time we have left, we'll solve some projectiles. Okay. And so due date's coming up. Since tomorrow we're doing the lab instead, I'll kind of bump the AP Classroom to Friday. So I did bump the due date on that. Okay. So you guys remember AP Classroom Unit 1, multiple choice questions? Okay. So no, those are going to be due Friday morning. We'll cover those on Friday. Your linear motion take-home quiz will also be due on that day. So here's what it looks like, right? Your linear motion take-home quiz. There's different versions floating around, but they're all about equally difficult. And then your chapter 3 puzzles. Your chapter 3 is two-dimensional motion. So it's just one that I circled. They're all projectiles except for this one. This is the only non-projectile. So I think if we get class time of class today, I'll walk you guys through that one. So we'll see how the time pans out there. All right. And then other stuff going on in the school. Photographs are going to be taken on Monday through your English classes, unless you're a senior. If you're a senior, it's some independent deal. But if you're grades 9 through 11, so they're taking on 9-11. There you go. Right, so, and then open house is going to be next Wednesday. So 1 week from now. All right. So you guys good with what's going on here? All right. So switch my screen over. And oh, look at all you guys hopped on to the Kahoot. Oh, yeah. Okay. So if you wanted to follow along, these questions are printed on the back side of. Remember, I gave you guys the honors page, the boxes on it. Okay. On the back side of that page are the conceptual questions that are the same ones that you guys are about to see here. All right. So here we go. You can still hop on after I hit start. So. No. Right. A vector is a quantity that has both what and a what. Oh. It's yellow. Yeah, a magnitude and a direction. So magnitude is like a quantity, like how much, right? It also has a unit on it, right? So like 3 meters per second, 20 meters, right? And also a direction associated with it. Right. So guys, what would be an example of a vector? Like, is velocity a vector? Is velocity a vector? Yeah, because it has magnitude and a direction. Right. What about time? Is time a vector? Time is considered to be a scalar quantity, even though I guess you could say forwards backwards, but yeah, time is considered to be a scalar. What do you think mass is considered to be? A vector or a scalar? Scalar, right? Because mass doesn't have a direction associated with it. Now, if you think about weight, is weight a downward force? Yeah, and that would then make it a what? A scalar or vector. So weight would be a vector, right? Okay, so if there's a direction, sometimes the direction is implied, then that makes it a vector quantity. Oh, yeah. There you go, right? I think the very first day of school, I gave you guys some printed pages. Somewhere on those, there's printed some examples of some scalars and some examples of some vectors. A scalar, for example, mass, is a quantity that only has a magnitude. So you might say the mass is equal to 3 kilograms, but there's no direction associated with that. All right. I got Jacob, Gavin, Matthew, and Neil. Oh, leading by 1 point. Ooh, all right. Suppose a plane can fly 100 kilometers an hour. It gets a boost from a 60 kilometer an hour tailwind. Now what is its ground speed? Ah, there you go. Yeah. Right. So now compared to the ground, it's moving really fast. Right. So you can add those vectors tip to tail. The resultant would be 160 kilometers per hour. You saw Paul Hewitt do a really similar one yesterday. All right, Matthew, move it to the top. What is the resultance of 3-unit vector and a 4-unit vector at right angles to each other? At right angles. What's the resultant? All right, 5 units. Here, let me switch over and draw that one out on paper real fast, just in case you should follow that. Okay. So you're right, it is Pythagorean, isn't it? So it's supposed to like 3 meters per second that way, and like 4 meters per second that way, right? Oh, notice I add those tip to tail. Do you guys see tip to tail right there? Right. So if you go from the tail of the first one to the tip of the last one, here's your resultant right there. Here's your resultant, right? And that would be 5 meters per second in this case. You could do Pythagorean theorem, right? Who remembers what is this angle right here? 53 degrees, winner. What is this angle right here? 37 degrees. Oh yeah. Oh yeah. All right. You guys are remember it. All right.
Oh yeah. Yeah.
Plane flying into a headwind loses ground speed. Plane flying with a tailwind gains ground speed. But what if there's a crosswind below 90 degrees? What happens to the ground speed? Uh, okay, most of you guys got that. The overall ground speed does increase. So this was also one of the polyhit things yesterday. In fact, I can use this to explain it. Suppose the plane can fly 3 meters per second. Maybe it's real slow, like little drone or something, right? Fly 3 meters per second straight north, right? And there's a crosswind blowing 4 meters per second to the east, right? Well, it's like the entire air mass is moving to the east at 4 meters per second. So what is that little drone doing compared to the ground? Well, it's going kind of northeast, actually at this 53-degree angle, east to north, right? And if somebody on the ground points a radar gun up at it, that radar gun is going to read 5 meters per second. Ah, you guys see that? Right? So it's going faster compared to the ground than it could just by itself in the still air. Ah, okay. If you're following shadow across the ground, the shadow is moving at 5 meters per second across the ground. Whoa, all right, we got Jacob, Matthew, Jacob, Kevin, Neil in the lead. Ball is thrown into the air at some angle. At the top of the ball's path, its velocity is 40. Yeah, entirely horizontal, right? Here, let's switch over and show you guys. Right. I'll review this with you guys too, but let's just look at the parabola path, right? So you blast the cannonball at some angle, goes into this parabola path, right? But at the very top, isn't it moving strictly horizontally? Just moved it strictly horizontally, right at the very top. Okay, you guys remember that?
Come on, Matthew. Come back.
Ball is thrown to the air at some angle. During the first second, it moves 5 meters horizontally. How far horizontally in the next second? Yeah, 5 meters. Because doesn't have a. We're talking about the horizontal motion, right? Because does that ball accelerate horizontally? No, only vertically. Gravity only pulls vertically. Horizontally, it's just constant velocity all the way across. It's going 5 meters per second, 5 meters per second, 5 meters per second, right? Horizontally, right? So it's going across the field at constant velocity. All right, Neil on fire in the lead. Projectile maintains its horizontal component of speed because it's not acted on by any. Yeah, horizontal forces. There you go. It's kind of an X unit concept. Right. There you go. Right. Now, guys, is there a vertical force on a projectile? Yeah, its own weight. So the gravity force, its weight, right? But there's no horizontal forces unless you think about air drag. But you guys know we ignore air drag in this class, right? All right, we got Kyrie, Rose, Gavin, Jacob, and Neil on fire. What part of a path does a projectile have minimum speed? Oh, there you go, top of its path. So as it's kind of on the way up, it's slowing down. And then when it's kind of falling down-ish, it's speeding up. The top of its path, it's moving entirely horizontally. There's minimum speed. All right, all right. Cannon fires the cannonball horizontally off a cliff at 30 meters per second. How far horizontally does the cannonball move in 1 second? It's on horizontal motion. Yeah, 30 meters. So every second it's moving 30 meters horizontally. Right? Now vertically, it's a more complicated story. Guys, how far vertically does it move in 1 second? Or let's say during the first second. 5 meters. Doesn't it fall 5 meters in the first second? And then how far total in the first 2 seconds? Like 20 meters. How far total in the first 5 seconds? About 125 meters. But how would you know that? College. So h equals 1/2 gt squared, right? So that's the vertical stuff. It's easier to hit a home run in Denver, Colorado than Miami, Florida. True, because why? Yeah, there you go. So thin atmosphere. How many of you guys been like a mile high way up in the mountains? It's really hard to run around, right? Yeah, really thin atmosphere. In the absence of air resistance, the optimal angle to throw a ball the furthest distance. Ooh, take your best guess. Take your best guess. Oh, look at you guys go. Look at you guys go. All right. Because I don't think I even told you guys that. Here, let me kind of explain it though. So, right. So, guys, if you took this cannon and you aim it straight horizontal, like 0 degrees to the horizontal, it's going to pretty much immediately hit the ground, like, not go anywhere, right? As you increase the angle, right, well, it's going to go further and further, right? But because it's in the air for a longer time, right? Now, there's this trade-off, though. Like, if you aim it straight horizontal, it's just going to come back and, like, fall back into the cannon, like destroy the cannon. Right? So, and it'll have 0 horizontal displacement there. So even though it's in the air for maximum time, well, it has no like forward component of its velocity. So there's a trade-off. And in the optimal angle to get the maximum horizontal displacement turns out to be a 45-degree angle. You could prove that. Okay. I can't help myself. I have to show you guys why. I'll show you guys why. Where's my posters? Hold on a minute. All right. So this is one you guys saw near the end of class yesterday. No, it's a fun proof to show like why this is the case, but that's through trigonometry. Let me draw a graph for you guys here. Okay. So suppose you said as a function of the angle from the horizontal angle, say in degrees, right? Could go from 0 to 90 degrees, right? 90 degrees from the horizontal beam, it's straight up. Okay. You want to know what is the horizontal displacement? Maybe this is in degrees and this is in meters, right? Okay. Now, if you aim the cannon straight horizontal, it goes pretty much nowhere before it hits ground. If you aim it straight vertical, it's just going to come back and land where it started, which is 0 horizontal displacement, right? Now, all in between, well, it's going to go further and further, and then eventually going to come back, right? Now, this it might look like a parabola. It's not a parabola. It's part of a sine curve. It's part of a sine curve, right? And you can show that here. This right here. Do you guys see how the slope, guys, the slope was the rate of change, isn't it? You guys see the rate change of distance with respect to angle, right, is positive until it goes to 0. Okay. Where the rate change of displacement as a function of the angle, that rate change goes to 0, that tells you it's no longer gaining distance, and afterwards it starts actually losing distance because the slope goes negative, right? Okay. So when you guys are in calculus and you're solving optimization problems, because this is an optimization question, like what's the optimal angle for the first distance, right? That's actually how you solve it, is you take the rate change, set it equal to 0, or you set the slope equal to 0, and then you can prove that in this case it's a 45-degree angle. So I don't know, I might do that with you guys someday, but just give you guys the big picture right there. All right, let's flip back over to Kahoot. All right, so good call on 45 degrees to the horizontal. Points all around. Cannonball launched at 30 meters per second on a flat terrain at whatever angle. It will land at a speed of what? You launch it at some angle, it slows on the way up, speeds up on the way down, lands at the same speed that you launched it. There you go, right? So it's slowed down on the way up, speeding up on the way down. Equal speeds at equal elevations. That's a symmetry question. You guys nailed it. Oh, yeah. All right. Projectile launched horizontally, hits the ground in 1 second. If it had been launched at a faster speed, the hang time. So you're launching it horizontally. What if you launched it faster? All right. So most of you got that. Most of you got that. Okay.
Oh, shoot.
Let's flip back over here. So tomorrow I will have you guys outside on the balcony, and you'll be doing this type setup. Right. So here's the cannon, right? And notice the cannon's aimed horizontally. So you're gonna launch it with some like V0 horizontally, right? And it goes like lands right there. Okay. What if you launch it with twice the speed? Guys, if you launch it with twice the speed, is it the same? Is it the same hang time? Same hang time, right? Right? How many of you guys think if it goes twice the speed, it'll go twice as far? Do you guys think? Right? Because guys, suppose this is a 5-meter drop. Guys, if it's a 5-meter drop, how much time does it take to fall? 1 second, right? It takes 1 second to fall 5 meters. So if you launch it like 20 meters per second, I'm just making up a number. Do you think it would land 20 meters out? Well, if you double that to 40 meters per second, would it be like 40 meters out, right? But what if you launch like cannon side by side, and at the same time you drop the ball, it just falls straight down, right? Do all those three, bam, hit the ground at the same time? Yeah, it takes them 1 second to hit the ground. They all have the same possibility.
That's 30 meters per second horizontally.
Right. Yeah, 30 meters per second horizontally. There you go. All right. All right. Hey, you guys are doing really good with these central questions. I got Rose on fire, Jacob, Neil, Gavin in the lead. Object thrown horizontally at 30 meters per second off the top of a cliff. What is its acceleration in free fall? Oh, everybody getting points, 100%. Oh, yeah. You know what? Actually, I'm glad you mentioned that. Here, let's switch back over here. So let's go to that last question because yeah, Nathan's bringing up a really good point here. Okay. What if you launched a bullet that was like hundreds of miles an hour or something crazy, right? Right. It would yes still hit the ground at the same time as long as you assume that there's like the the Earth is flat, which is like approximately true locally, right? Right, guys. What if you get going like, oh, let's call it about 8,000 meters per second? Then you start to run into problems because at some point you're going to start falling around the curvature of the Earth. You're going to start going to orbit. There is such a thing as like orbital speed. So and orbital speed ends up being about 8,000 meters per second. So yeah, if you fired something at 8,000 meters per second, it would actually fall around the curvature of the Earth. It would never actually land. Yeah, but if you anything short of like an orbital speed, yeah, it's going to hit the ground. You can assume the same time. We're assuming a flat terrain and nothing close to orbital speed. Yeah. True. All right. Neglecting air drag. What's the point? Acceleration is greatest for a ball thrown straight up vertical. Acceleration. Right after it leaves your hand. Yeah. It's always, guys, acceleration for anything in free fall is always 10 meters per second squared downward, right? It doesn't matter how fast it's going, which direction it's going, right? Once it's in free fall. There you go. Suppose you can jump 1 meter vertically. Now, what if you're on a skateboard that's moving 50 meters per second horizontally? Can you jump what? The skateboard's moving horizontally. How high can you jump now? All right, you guys got that. So horizontal motion, vertical motion, keep those independent. You guys got it. When in orbit, a satellite such as a space shuttle, ooh. Why the font's so small today. All right, you guys got that one too. Yeah. So the actually up at like low Earth orbit, there's about 90% of the gravity field that there is down here on the surface. So the gravity field actually isn't that different. Yeah, so there's definitely gravity force. Guys, the fact that it's on a curved path means the direction of the motion is changing. So there is a force on it. Okay. Yeah, you could think of it as just a projectile that's falling around the curve of the Earth. So interesting kind of projectile, right? It actually wouldn't be a parabola path anymore. Maybe more like either a circle or an ellipse. All right. Ball thrown straight up at 20 meters per second will return to the ground with the speed of. All right. So you can get that by symmetry, right? So equal heights, equal speeds, right? Ooh, I got a different question for you guys. Guys, how much time does it take for that to reach the peak?
2 seconds.
2 seconds, right? Because it's slowing down 10 meters per second every second as it's going up. Okay, so what's its total hang time? But what time comes back to your hand? What's the total hang time? 4 seconds, right? Because 2 seconds up, 2 seconds down, right? You guys got this, right? What's the maximum height? It does end up being 20 meters because if you run h equals 1/2 gt squared and you plug in 2 seconds, because it could be like falling for 2 seconds. Yeah, that does come out to be 20 meters, right? Right, guys remember that? That goes through the college equation. Right. All right, we got Mector, Rose, Jacob, Neil, Gavin going to for the win. Cannon with barrel velocity 120 meters per second launches horizontally from the top of a cliff. How far does the ball fall in 3 seconds? How far does it fall in 3 seconds? All right, 45 meters. Okay, guys, does the 120 meters per second horizontal speed have anything to do with the answer? No, because they just dropped the cannonball from the edge of the cliff. How far does anything fall in 3 seconds? 45 meters. Can you do h equals 1/2 gt squared? Right? 3 squared is 3 seconds squared. It's 9. 9 times 5. Yeah, 45 meters. That's the college equation. Right? Now, if you pick the green one, 360 meters, that represents maybe it's horizontal displacement, how far it goes in 3 seconds across. Right? Right? Right. All right, let's check out winner podium. With the bronze, Rose. With the silver, Neil. And the gold, Gavin. All right. Runners up. Got Jacob and nice job. Nice job. All right, let's switch back over here. All right, so I think one of the last things you guys saw yesterday was this. Maybe it was like this bell was about to be written. So here, let me walk you guys through this projectile again. Because it's actually not too dissimilar from the FRQ we're going to walk through here in a minute. Okay. Suppose you blast a cannonball at 100 meters per second at a 37-degree angle from the horizontal. And the question is going to be, where does the ball land? You could ask other questions too, like how high does it go or something like that. But here, let's just for now focus on where's the ball land. Okay. So we did go through this one yesterday. Now, these projectiles are always process problems, and you're juggling two different dimensions. You got a height dimension, and you got a horizontal dimension, right? It's got the y direction, the x direction. Okay. Okay. Now, the first thing I'm going to do is I'm going to take that blast velocity, I'm going to break it into components. Say, well, see, it's partially across and partially up. Right, guys, how do you get how fast it's going across? Take 100 meters per second, multiply by what of 37 degrees? Cosine, right? See, we're going from hypotenuse to adjacent. You guys see that right triangle right there, right? Hypotenuse to adjacent, that's cosine, right? And that comes out to be 80 meters per second, okay? And then how do you get the initial vertical component of velocity? 100 meters per second times what? Sine of 37 degrees. See how it's opposite of the 37 degrees, right? And that comes out to be 60 meters per second, right? Now, the horizontal component, 80 meters per second, that stays the same all the way across. But what about that 60 meters per second initial vertical velocity? Does the vertical velocity change? All the time. It changes 2 meters per second every second. In fact, after 1 second, how fast is it moving up? 50 meters per second. And then 1 second later, 40. How many seconds does it take to get to the peak? 6. Guys, if it takes 6 seconds to get to the top, how many seconds to get back to the bottom? 6. And what's the total hang time? 12 seconds, right? Now, I'm using nice whole numbers for this case, right? There's a 3, 4, 5 triangle. It's convenient. We got, but yeah, it's a little bit funny numbers. You could run the equations, get the same results, right? All right. So now going back to horizontal motion, then we know it's going across the field at 80 meters per second. We know it's going to be in the air for 12 seconds. Can you just multiply those two and get the horizontal displacement? Boom, boom, just like that, right? Alternatively, if you use this range formula here, you just plug it in. The blast speed squared divided by gravity, field times sine is 2 times the angle. You get the same answer basically. Okay, so that. All right, so that's a reminder. Something you guys saw yesterday. All right, you guys ready for this FRQ? All right, so there's a printed page on your desk. So I'll walk through that.